And let's get started on Lumberjack lesson number 1 here. We are on 5.4. We're looking at logs and the log function. So first thing, let's get started here. How are those two graphs related? We've got x squared, where x is greater than or equal to 0. We've restricted the domain to just the right side of that blue graph to give us the top part of that inverse. Notice that they are inverses of each other. Okay, and we've seen those before. Right there is your y equals x. They all intersect right on that line. If we take some points, such as, let's take 2, 4 on the original, becomes on the red one 4, 2. And that was our inverse. So today's lesson is a continuation of inverses, really in its graphical form. Let's look at 2 to the x. We've dealt with exponentials. Okay, so let's graph that one. Let's plug in our y values here. Okay, so the first one, 2 to the negative 2, that's 0.25, or 1/4. Okay, 2 to the negative 1, that's 1 over 2, that's 0.5. 2 to the 0, everything to the 0 is 1. 2 to the 1 is 2, then 4, then 8. And let's plot those down. So let's put some axes on there and number it up. Put on our dots. And then join those dots, label the graph. We've got y equals 2 to the x. Let's put in our, because we're doing an inverse, we got to put in our reflection line, which is y equals x. Put that one in there. And that goes right through 0 and 0, 1, 1, 2, 2, all the way along. So now to plot those points, we're going to take, instead of negative 2, 0.25, we're just going to do the inverse. 0.25, negative 2. And do that with all of the points. So we've flipped all the x and the y's and to change the x and y's on all the points there now. Let's plot them and connect the dots. There's all the points. And connecting them, we get that blue graph. Notice here, we're doing the inverse, x equals 2 to the y. Now the really important part here is looking at where's the asymptotes, where's the domain, where's the range. So let's start with the original. I'll do it all in red here. So first of all, our asymptote, the y equals 2 to the x. The asymptote, that was the x-axis. So y equals 0. Our domain was XER. Our range, well, that was everything above the x-axis. So it was y is greater than 0. If we're doing our inverse, that means everything flips. The domain becomes our range, our x-intercepts become y-intercepts, our asymptotes go from horizontal to vertical and vertical to horizontal. So now we've got x equals 2 to the y. Our asymptote now is not y equals 0. We switched x's and y's. It's now x equals 0. Our domain and our range switch. So our domain originally was XER. Our range is now YER. Just switch the x's and the y's. Our range was y is greater than 0. So our domain is x is greater than 0 now. So if you struggled with any of those inverse information that we did there, please look back at your 3.5. That's where we did inverses. So inverses were at 3.5 there. So now term logarithm, and that's what we're looking at here. We're looking at logs. Is used to describe the inverse of a power. Whoa. For example, the inverse of 10 to the x is going to be logarithm to the base of 10 of x, which is written as this, but we say log base 10 of x. Well, let's look at kind of the reason why we're going to be doing this first. I'm going to take you back to 5.3, where we did our opening activity there. You had a question that said 2 to the x equals 32. What's the value of x? And we could do a little bit of guess and check there and see, oh, we need to get these both to a common base. Common base of 2 and 2 to the 5. At this point, we were able to say that x equals 5. And then the question was asked, well, what about 2 to the x equals 12? The only way to solve that was graphically. Graph one side, graph the other side, find the intersection point. The reason we can't do it algebraically at that point is that we can't get these both to a common base. So we can't get to a common base, because you didn't have the algebra skill to do it at that point. However, in walks logarithms. Logarithms are that algebraic link that allow you to do a question of this type now. So that's where we're going with it. Let's look at graphically first. Oops. Okay, so here's the graph of y equals 10 to the x. That's the red one right there that you can see. And let's look at its inverse now. So that means we've got to have our y equals x line and then our inverse. The inverse of an exponential function is a log function. So 10 to the x, the inverse is log base 10 of x. So each graph is a reflection of the other graph in the line y equals x. And this is going to hold true for all exponential functions. So if we were 2 to the x, y equals 2 to the x, the inverse function would be, well, in order to do our inverse, switch your x and your y, x equals 2 to the y, and re-solve for y. Up to this point, you haven't had any algebra skills to be able to re-solve for y from here. The way we do it is we take it into a log form, where we go y equals log base 2 of x. And I'll show you that process in a moment here. But first, it's about time to put something down here. Okay, there are better ways to log off. I know I was feeling that way with the computer the other day, that's for sure. Okay, so to understand what a logarithm is, consider the coordinates of corresponding points on these two graphs. Start with the first one. We know 10 to the x. We can work with that. If we go 10 to the 0, we know that that's going to be 1. So therefore, our point's 0, 1. 10 to the 1, that's 10, 1, 10. And 10 to the 2 is 2, 100. If the log graph is the inverse, that means our x's and y's have to switch. So if our answer was 1 here, our new input is going to be 1. It's got to go back the other direction and get us back to 0. So log base 10 of 1 has to be 0. Log base 10 of 10. Well, again, it has to be 1. We have no choice on that. Log base 10 of 100 is equal to 2. Huh, interesting. Let's just look at an aside here that 10 to the 2 is equal to 100. So I could say log base 10 of 10 to the 2. That equals 2. Just for the fun of it, I want you to try to figure out, what do you think log base 10 of 1,000 would equal? Log base 10 of 1,000, that's the same thing as log base 10 of 10 cubed. Ooh, starting to see a pattern there. That's going to be equal to 3. And that's what I was saying there. That log base 10 of 100 equals 2. That means that 10 to the exponent of 2 is equal to 100. That's what we're saying. The 10 raised to the power of 2 equals 100. Which brings us to the chart at the bottom of the page there now. Looking at this, This b here is the base. It's the same base of the exponent. That's our base. The c, or sorry, the a I mean, is our exponents. So really what we're saying here is a logarithm is talking about an exponent. Whenever we talk about a log, we're talking about the exponent. For instance, log base 10 of 100. What exponent on 10 would give us this? The exponent is 2. Now, of course, we've got some restrictions on these. That b has to be greater than 0. We discussed that. B can't be equal to 1. And the c value has to be greater than 0. These are just our restrictions on our domains and ranges. All right, your turn. Can you do this without first doing one? Just looking at that, answer that one up for yourself. All right, now that you've had a chance to try one out, and we're going to do a bit more instruction on it. First thing you always want to remember, when you're converting and you're changing between an exponential form and a logarithmic form. Right now, this is the exponential form. We're going to change it to the log form. Both of them are identical. They're talking about the same thing, just talking from two different points of view. The base is the base is the base is always the base. Whatever the base of the exponential form is going to be the base of the log form. Best thing is to do is identify your base. It's going to be this 3. So we can start right there. We know it's going to be in log form, a log base 3. That's a little bit of a smaller 3. It's a subscript, so it is a little bit lower and it's smaller. So log base 3 of something equals the exponent. Whatever the log is, always equals the exponent. So the exponent was that 3 over here. This 3 went here. That 3 went over there. And the 27 is going to come down into here. So it says log base 3 of 27 is equal to 3. Or in other words, 3 to the 3 is equal to 27. Let's try the next one. Okay. The base is the base. The base was 5. So we're going to say log of 5. We know that the exponent goes on the other side by itself, equals negative 2. And the 125 goes on this side. The base stays as the base. And then the other two numbers switch sides as we do our inverse. So the 2 goes to one side, and the 125 comes to the other side. So the 5 and the 125 were on opposite sides before. Now they're on the same side of the equation. The 5 and the negative 2 were on the same side. Now they're on opposite sides. And we know that 4 to the 0 is equal to 1. So let's do this one again. Log of 4. Log base 4. The base stays as the base. The base was 4. The base is 4. Now the 0 and the 1, they've got to switch sides where they were with the 4. The 0 was with the 4. Now it's got to be on the opposite side. The 1 was on the opposite side. Now it's on the same side with the 4. And again, this is saying 4 to the 0 equals 1. Let's go in the other direction. The base stays as the base. The base was 7. So therefore, 7 to the exponent. The log is equal to the exponent. So again, this is the exponent on this side. We're taking it from the log form, changing it into exponential form. The exponent goes now with the base is equal to 49. Oh, that's true. 7 squared is 49. Yeah, we know that. Next one. The base stays as the base. The base was 4, So we got 4 to the negative 3 is equal to 1 over 64. Okay, base stays as the base. 10 to the negative 4 equals 1 over 10,000. Now, I better make a point right now before we get any further. If we went back to this information right here, we said that the C value has to be greater than 0. That means we cannot take the log of a negative number. So cannot take log of negative number. The reason for that is because when we did our exponential, we couldn't make a negative number when we had our exponents. Or in other words, originally it was all the y values were greater than 0. Now, all the x values are greater than 0. We cannot take the log of a negative number. However, that does not mean that the log cannot equal a negative number. We just cannot take the log of a negative number. These in blue always have to be positive. Our whole number system is based on 10. 10 because of 10 fingers. That way we can count how many animals we own on our fingers. Our base of our number system is 10. There are other number systems that are not base 10. Binary, base 2. There's another older computer-based system, which was octal, and it used the numbers 0 to 7, so it was a base 8. Hexadecimal, especially those of you who have done HTML and web page design, hexadecimal uses 0 to 9 and A, B, C, D, E, F. That's 16. It's a base 16 language. We use in mathematics a base 10 mostly. So because our number system is base 10, and we use a log base 10 so often, we're going to call that the common logarithm. That button's stored into your calculator. All of the log base 10 numbers are sitting there. Someone programmed them in for you. So you don't have to use a table. Before electronic calculators, they had to use a table to look these numbers up. So when logarithms to base 10 are written, the base is often not shown. It's like when we do a square root, we don't put the index of a squared. We just say the square root. Same thing with a log. We don't have to put log base 10, we can just say the log of x. Your log button on your scientific calculator is sitting right beside the number 7 on the TI-83 or 84 series. So if you're trying to solve a log problem and it's base 10, you can use your calculator and get the answer. However, if you have other bases other than 10, you've got to use some other strategies. For instance, log base 2 of 2 to the 3. Okay, we've kind of looked at this. We use base 10 though. And what we're saying is the power to which 2 is raised to get 2 to the 3 was 3. So we're saying 2 to the what equals 2 cubed. That's really what we're saying. We're saying 2 to the what equals 2 cubed. Oh, that what is the 3. In this next one, we're saying again, same thing. 4 to the what is equal to 4 to the 6. 4 to the what equals 4 to the 6. Well, obviously it has to equal 6. So a good strategy that we're going to be looking at is trying to get bases to be the same, just like we did with the exponential. So the first of many laws that you're going to need to know, just like there's exponent laws, first of many of the logarithm laws is that log base b of b to the n is always going to be n. And one of the things that we've already looked at in this course is that if we're looking at the composition of functions, if it equals x, or in this case n, because we're using the letter n, if it equals x, then those two functions were inverses of each other. It's a way to prove that two things are inverses. So if we take g of x and stuff it into f of x, we're going to get x, or in this case we're using n here. So when we put it in and we get n, that means they must be inverses. Same thing, if we stuff f into g, it's going to be x, or n. Proves that it is an inverse. Okay, you got to be able to now take what I just talked about, and let's see if you can hammer this one in. Base 7 of 7 to the 14, what's the answer to that one? And let's use what we've just learned. Log base 5 of 3125. Got to be equal to something. It's not a base 10. We can't just go and punch it into our calculator. But we can try to get a common base. So if we can get log base 5 of 5 to something, we know that that something is what it's going to equal. So we just take a little bit of guess and check and say, okay, 5 to the what equals 3125. And as we plug it in, punch it in, and we finally say, oh, 5 to the 5 is 3125. So that the whole thing will equal 5. Looking at the next one, got to get it to a base 6. So log base 6. And we know it's 1 over 216. So that means we're going to have a negative exponent here to flip that. So 6 to the negative something. So 216 is equal to 6 to the, punching it through, guess and check. Oh, that's 3. So 1 over 216 is 6 to the negative 3. So this equals negative 3. Oh boy, getting real tricky now here. We've got log base 8 of 2 times the cube root of 2. Ay, ay, ay. Let's do some cleanup of this mess. So what we're really trying to do is get 2 root, the third root of 2. We got to get that into a base of 8. 8 to the something. Because we've got a base 8 on this log. Oh, well, let's try to combine it together because they're both at a 2. So let's work with that first. So this is 2 to the 1 times 2 to the cube root is 1/3 as an exponent. Multiplying like bases, oh, this is why we had to go through all those exponential rules, because we're going to have to use them in lots of these questions. 2 to the 1 times 2 to the 1/3. We add the exponents. So that's 2 to the 1 plus 1/3 gives us 4/3. So now we've combined them. We now have to turn this 2 into an 8. But I kind of know something about 2's and 8's. They are related. I know that the cube root of 8 is 2. The cube root of 8 is 2. So I can, instead of saying 2, I can say the cube root of 8. Let's take that to an exponent because we want to deal with exponents all the way through. That's 8 to the 1/3. That's the same thing as 2. Let's substitute that in for the 2 instead. So 2 is 8 to the 1/3 to the 4/3. All I did was substituted the 2 with another version of it. Now I've got an exponent of an exponent. Oh boy, we're using all these rules in our bag of tricks here. And multiply the exponents. That gives us 8 to the 4/9. Let's bring that back in to our log. So now we're substituting that with this, because those are equivalent, just looking different. So log base 8 of 8 to the 4/9, and that exponent there is what it equals. So it's going to equal 4/9. The whole original question was equal to 4/9. But this strategy only works if we can get that number into a base that's the same as the base on the log. If we could get it into a base 5, or into a base 6, or into a base 8. But what happens when we can't? We're going to have to estimate right now. We're going to use some benchmarks. So we're looking at a base of 5. So I'm going to take anything that's a base of 5 on either side of 100. I know that 5 squared is 25. I also know that 5 cubed is equal to 125. So 100 is somewhere in between 25 and 125. That means that the log base 5 of 25, which is 5 squared, and log base 5 of 125, which is 5 cubed. My answer has to somewhere be between 2 and 3. So it's going to be 2 point something, and 100 is much closer to 125 than it is to 25. So let's say, hey, maybe it's 2.8, 2.9, somewhere's in there. And you can then, at that point, take your calculator and say 5 to the 2.8 or 5 to the 2.9. Punch them into the calculator, and you'll see that this is 90.5974. And 5 to the 2.9 is 106.4174. So it seems to be a little bit closer to 2.9, so I'll use 2.9 as my approximate answer. Okay, we can't plug this one into the calculator yet. So we're going to have to, in order to graph it, let's use things that we know that are a base 4. So let's make a table of values. An x, y graph. I know things that are base 4. I could say 4. I could say 16, because I know 4 to the 1 is 16. I know 4 squared is, 4 to the 1 is 4. 4 squared is 16. So let's start with those ones. And we say, okay, my x is log base 4 of 16, which is the same thing as saying log base 4 of 4 squared. So it's equal to 2. Log base 4 of 4 to the 1 is 4. 4 to the what is equal to 1? 4 to the 0 equals 1. 4 to the what equals 1/4? Well, -1. 4 to the -1 equals 1/4. And then 4 to the what equals, let's choose 1/16. I know it's -2. So we're going to graph each one of those points there. As I plot those points, you can see now there's your graph right there. And now there's an asymptote at the y-axis, so there's no y-intercept. The x-axis, we can just read that x-intercept straight off of our chart here. So our x-intercept has to be then, when the y is 0, it's at 1. Our domain. We know that the domain was everything to the right of our y-axis. So we've got x is greater than 0. Our range. Our range, we can have any y values. It's xer. And the last thing, just to identify, we have to identify where is that asymptote. We know that the asymptote is the y-axis. So asymptote at x equals 0. And all these properties here that we just went through from the graph are going to be represented in all of them, all the way through. It is the inverse of the exponential function. And again, answer your last 3 questions up for yourself to see if you